All right, welcome. Today we're going to dive deep into one of the most fundamental graph algorithms out there, depth first search, DFS. Seriously, by the end of this, you'll get exactly how it works, how you can code it up, and where it's actually used in the real world. So let's just jump right in. So let me ask you something. Imagine you're dropped into a giant, sprawling maze. How do you find your way out? I mean, what's your strategy? Well, you'd probably just pick a path and follow it, right? You'd go all the way down until you hit a dead end. Then, you'd backtrack a little bit, just enough to try the next turn you ignored. And you'd repeat that. Well, guess what? That intuition, that exact process, is the core idea behind what we're talking about today. And that brings us to the formal definition, but it's super simple. Depth-first search is all about going as deep as you possibly can down a single path before you're forced to turn back. The best analogy I can think of is exploring folders on your computer. You double-click a folder, then another inside that, and another. You keep going deeper and deeper down one path until you either find your file or you hit a dead end. Then what do? You go back up one level and try the next folder in line. That's DFS in a nutshell.
Okay, so let's really dig into the core idea of how DFS operates.
When you get down to it, the whole algorithm is just three simple rules. First, you get to a node and you visit it. That just means you do whatever you need to do there, maybe print its name or check if it's your destination. Second, and this is the most important part, you have to mark that node as visited. You got to leave a little flag or something so you don't come back and get stuck in an endless loop. And third, you look at its neighbors, find one you haven't been to yet, and you do the exact same process all over again from there. It's a beautiful recursive chain reaction.
Okay, but wait a minute. How does the algorithm remember where to backtrack to? I mean, what's its memory? Well, the secret lies in a very specific data structure. The secret ingredient is the stack. Now, what's a stack? Just think of a stack of plates. The last plate you put on top is the first one you take off. It's a last-in, first-out deal. And that's perfect for DFS, isn't it? The last path you went down is the first one you need to remember when it's time to backtrack. Now, there are two ways to get this done. The most common way is with recursion, where the function calls itself. The programming language handles the stack for you automatically. It's called the call stack. Super clean. The other way is to build and manage the stack yourself, manually. This is called the explicit stack, and it's really useful for avoiding some tricky problems. Okay, enough theory, let's get into the code. And you're going to see that it's a direct, almost word-for-word translation of the logic we just talked about. So here's the classic recursive approach, the one you'll see most often. Look how clean this is. The function takes the current node and our visited tracker. The first thing it does, it marks the current node as visited. Then it loops through all of that node's neighbors, and for any neighbor it hasn't seen yet, it just calls itself. That's it. That simple pattern, mark, then recurse on neighbors, is the entire engine of recursive DFS. So the recursive way is great, it's beautiful, but it has a potential weakness. What happens if your graph is just ridiculously deep? Imagine a path that's millions of nodes long. Well, every one of those recursive calls gets added to the program's internal memory stack. Eventually, you can literally run out of memory for it. This is the classic Stack Overflow error. So what do we do when that's a risk? Well, the solution is to do it ourselves. We use the iterative approach. Instead of relying on recursion, we create our own stack. We kick things off by pushing our starting node onto it. Then we start a loop that runs as long as there's anything on the stack. Inside the loop, we pop a node off the top, we process it, and here's the important part. We find its unvisited neighbors and push them onto the stack. This gives us the exact same deep-diving behavior, but completely avoids the risk of a stack overflow. Okay, so now we know how it works and how to write the code. But where do you actually use this thing? Let's zoom out a bit and look at where DFS shines in the wild. So you pretty much can't talk about DFS without mentioning its sibling, breadth-first search, or BFS. They're like two sides of the same coin. The big difference is how they explore. BFS explores wide, level by level, using a queue. Think first in, first out. This is awesome because it guarantees you'll find the shortest path to something. DFS, as we know, goes deep using a stack, last in, first out. It's usually way more memory efficient, but there's absolutely no guarantee that the path it finds will be the shortest one. So how fast is it? The time complexity is written as O of V plus E. Now, that might look a little intimidating, but it's super straightforward. All it means is that the runtime is directly tied to the size of the graph. V is the number of vertices, the nodes, and E is the number of edges, the connections. To explore the whole graph, DFS has to touch every single node and every single edge once. It's incredibly efficient. You literally can't do it any faster. And what about memory? For space, it's just O of E. This is because the memory footprint is determined by the deepest path it explores. In the worst-case scenario, you could have a graph that's just one long chain of nodes. In that case, the stack would need to hold all the vertices. This is one of the biggest advantages of DFS, especially when you compare it to BFS, which sometimes has to hold an entire, massive layer of the graph in memory.
So because it's so efficient, DFS is incredibly versatile. It's like a Swiss Army knife for graph problems. I mean, yes, we've talked about solving mazes, but it's also the go-to algorithm for detecting cycles in a graph. It's fundamental to something called topological sorting, which is crucial for things like scheduling tasks that have dependencies. It's also used to find connected components, basically finding all these separate islands in a network. And it's the backbone for a whole class of problems solved with backtracking. It is truly a foundational tool. Okay. To wrap things up, let's talk about some practical advice, the tips, the common traps, and the big takeaways that'll help you use DFS effectively. So what are the common mistakes you need to avoid? Number one, by a long shot, is forgetting the visited array. If you don't track where you've been and the graph has a cycle, your code will get stuck in an infinite loop. It'll just ping-pong between nodes forever. Another classic is accidentally using a queue instead of a stack. You get your BFS and DFS logic mixed up. Just remember, depth-first search uses a stack, always. And now for some pro tips. My advice is to always prefer the recursive approach first. Why? Because it's just so much cleaner and easier to read. The code often directly mirrors the logic in your head. However, if you suspect you're dealing with a graph that could be incredibly deep, pivot to the iterative approach. It's your safety net against stack overflows. Oh, and for representing the graph itself, an adjacency list is pretty much the standard, best practice. So, what's the bottom line here? DFS isn't just some abstract algorithm you learn for an exam. It's a fundamental pattern for exploration. When you master the simple idea of going deep down a path and then backtracking systematically, you literally unlock solutions to a huge class of problems you couldn't solve before. It's a key that opens a ton of doors in programming and problem solving.
So I'll leave you with this to chew on. We know DFS explores a graph, and we use that visited list to avoid getting stuck in loops. But how could you tweak that logic to actually find a loop, to detect a cycle on purpose? What if you could tell the difference between a node you've already finished exploring and one that you're currently exploring on your current path? If you can answer that, you're well on your way to building a cycle detection algorithm. Thanks for joining me on this deep dive.